here, so I cherish this session. So agile focus. So before start, I ask Professor Akemichi for the opening remark. And then Akemichi is the first speaker. So
here is we have many young researchers, and I certainly suggest you to consider the purpose or why you are here, and to think about
exposed to the electrolyte actually dissolves in the cyclic operations, and therefore there is definitely a stability issue in using these materials. And like for the synthesis cannot always be perfect, and there will be definitely significant portion of particles that has the core exposed to the electrolyte, and therefore some additional enhancement in stability.
I see the speaker because the northernmost part of Japan is to the best of my knowledge, this is a pretty cold place. But at the end of the century, if we do these kinds of linear projections, we expect that the rice production will be actually.
If you look at the chemical industry, so if you look at the marketing growth expectation of cyanide, it's increasing next 2 decades. Our chemical, the heavily reliable on cyanide. So indeed cyanide needed for chemical industry. But biomass, I don't know, it must be toxic. 1 millimole is toxic or biomass.
Contact principle, broken positive powerful. But here, I just put the name of the material. This is not a physical chemical parameters. But if you plot it based on the absorption, the binary energy something, I think we can make that okay. But at this moment, just put the name of the material. Doesn't mean the related physical chemical parameters. That's why we could make the kind of okay about this.
Before diving into the rest of the things, I'd like to start by introducing briefly about my research background. One of my research background is basically focused on the water splitting reaction for making hydrogen. And many of you might already know, this water splitting reaction is consisting of 2 half reactions. At the anode, oxygen gases can be formed through the oxygen evolution reaction, and at the cathode, hydrogen gases can be formed through the hydrogen evolution reaction. And although the detailed electrochemical reaction can be a little bit different depending on the features of the
chemical pathways that led to what we now understand to be life today. I'm so confused that we often think about chemistry that is really non-biological. The system chemistry related to what we showed earlier is kind of activated nitrogen chemistry. Really cool to see the new results, right? Because I think some of the problems with these schemes is like, where do these compounds come from?
By asking many geographic questions about something, biology and chemical equation, I think that we can do many exciting information questions from the presentation today. So please thank you.
Thanks, you, and yes, please ask me questions. Let's piggyback to our prompting earlier, the first topic today, why are we here?
From stable organic compounds, these are sometimes very energy demanding. So in order to perform this electron transfer by using chemical oxidants, might be not compatible with very sensitive functional group. Or you need to also consider about the very fast back electron transfers based on Mark's figure. So in order to control this back electron transfer efficiently, there have been many efforts in recent efforts by unconventional means of molecular activation, such as organic photo redox catalysis or organic chemistry. So when you see the organic photo redox catalysis sample, this following excited species are engaged in the electron transfer, which can prevent or which makes you easier to control the back electron transfer because
hydrothermal system in the solar system or beyond, providing increasing evidence supporting this scenario and developing this scenario as a central subject in astrobiology. But from the chemical point of view, it remains very controversial whether metal sulfide really supported preservative chemistry. So although there are so many laboratory simulations studying the preservative rule of metal sulfide or preservative organic synthesis, so there are still many huge gaps in yield and selectivity and diversity between the
The network, hydrogen bonding network is really complex. It's just a picture, but it should be much more complex than this picture. So then, in the kind of natural water, for example, seawater, there's a lot of ions, many organic compounds are dissolved. So we cannot do something with just natural water. Because here is the water. We don't know what is the cause, where it came from. So, but I think the best way to do something with this kind of impure water is just increasing the amount of the one reactant. So this
If you look at that reaction, in order to activate one carbon, at least we need two hydrogen. Okay, so why? Or else then the result, the water is produced. So because of that simple reaction, in order to activate something containing carbon, if you start from the CO2, you need more hydrogen, but always we need two hydrogen. So if you look at the price of the green hydrogen, that's the required electricity, and then from there we can calculate how much. How much is it? Like in Korea, 1 kilowatt hour is about 10 cents, and then we can calculate.
So essentially, because we are in the same trend, we have the same fate, right? So we have to work together, right, to solve that problem. Probably Japan and Korea has a very successful story in the manufacturing industry.
And I really hope that everybody, especially I'm thinking about the students here, you can find the research that you're interested in and you're passionate about, and it can be fun. Or you find some other thing that's not research. It doesn't have to be research, of course, but I think when I look around here and I think about the people that were giving the talks today, I think we're all having a lot of fun in our research. And that's been a primary driver for me throughout my whole education and training. I never ever decided to become a professor, it just happened. And it happened because it's fun. And that's the real reason